Okay, let me start with Chapter 1, Sections 1.1 through 1.4. Just intro and some basic concept, basic terminology. So just some of the things we're going to look at, this idea of a system, which we need to define as we go through and do our analysis. We'll look at the three laws of thermodynamics, just do some review of the units and units conversions, the unit systems, SI or USCS system. Um, we'll look at work and energy, just some review of that. Define this idea of continuum. Okay, that's an important concept for us so we can handle, um, thermodynamic systems in a certain fashion. And then what's defined as intensive and extensive properties. Okay, first we'll start section 1-1, thermodynamics and energy. So here's a definition of thermodynamics, right? We're going to deal with heat, work, and temperature, and the relationship to energy, radiation, and properties of matter. Energy conversion, right? Well, that's one of the things we're going to do. Energy across what so-called boundaries. We'll take a look at that. Okay, so just defining, just from our terminology, what energy is, capacity to do work, right? And work is a process of transferring motion of an object, um, process of energy answer, right? Either you're doing work on something or something is doing work. Okay, so depending upon if it's positive or negative work, right? That will be the important part of that sign. So this is ability to do work, right? And we see energy in all sorts of forms, right? One of the main points or main laws, the things that we're going to deal with, is this idea of law of conservation of energy. One of our underlying principles, right? You can't create or destroy energy, right? You can only convert it from one form to another. Okay, so we'll look at that and how this relates to the laws of thermodynamics. Okay, so first law is just conservation of energy principle. It just says energy essentially is a thermodynamic property. Uh, you can't create or destroy energy, so when we do our analysis, we have to come up with a ledger and essentially account for all the energy in a system, right? So is it are we dissipating heat out into our environment? Are we taking heat energy in from our environment, right? We'd have to account for that. What's the energy change in our system? So essentially, we'd have to account for all of it, right? The second law of thermodynamics um, just basically talks about the direction, right? Decreasing quality. Energy is transferred in terms of from a higher quality source to a lower quality source. And we'll take a look at a few examples. The last one, the zeroth law, this talks about thermal equilibrium. All right. And the basic idea is you have two systems in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. Okay. And we'll take a quick look at a diagram for that. All right. First law of thermodynamics. Here's an example. If we neglect, any energy loss to heat, what we would say is that, like, let's say you have a boulder, has a certain amount of potential energy, you push it off a cliff, it starts traveling down. What happens? The kinetic energy increases and the potential energy decreases. But you'll notice that the overall energy, the total energy of the system is 10 units, right? And like I said, we ignore, um, what energy is lost due to heat when it's traveling through the wind. Okay. Here's another example. Let's say what this really says is essentially change in internal energy, delta U, right? And it's like whatever food you take in, that's your added energy. And here is like work that you do and heat that's being dissipated, right? And we've accounted for all those. Okay, so whatever change is left. So if the food energy is higher than this, then you have an increase in energy, internal energy. If, of course, your doing more work and radiating more energy than the food energy, then of course this is going to be negative. Okay, And then here's another one, just flour. It's like what the stored change in stored food energy. Okay, so whatever energy comes in for the sun, whatever you dissipate, and that becomes the change. All right, so those are just some examples, but it's all accounted for. Okay, all right. This is the first law of thermodynamics. Okay, conservation of energy, and then the second law of thermodynamics basically says the quality of energy. And here's two examples that I found. One is heat is high, at a higher temperature. Heat will travel from a higher temperature to a lower temperature. And eventually, what would happen in this case, of course, is that this coffee would become the same temperature as the environment, right? There'd be no more heat exchange with the environment. Here's another one. So you have from a high pressure, stored in a balloon, puncture it or whatever, open it up, and then it's going to go to a lower pressure. Okay. The third one, zeroth law, basic idea. Let's say that A is in thermal equilibrium B, A is also in thermal equilibrium C, then B and C are in thermal equilibrium. Okay. Okay. So classical versus statistical thermodynamics. It's just some terminology for us. Just that classical thermodynamics, you don't care about the individual particles. In statistical thermodynamics, you're basing, your analysis on the average behavior. Okay, so a little bit different. Here's some applications of thermodynamics. Okay, power plants, refrigeration, aircraft, same idea, right? Anything with an engine, of course. If there's a heat engine, let's say, or anything where you have fuel that you use, you burn it, you take the energy out of the fuel essentially to get motion in the aircraft. Human body, we looked at an example like that. Power plants, same kind of idea. And it's either, where are you getting the energy from? From nuclear power plant where you're superheating the system, superheating the water and making steam, and then you're using that steam to turn turbines. So you're taking that, essentially that thermal energy and using it to rotate, turbines, mechanical energy, and then you're taking that and creating electrical energy from that rotating turbine with a generator connected to that. Okay. Air conditioning, refrigeration, similar kind of concept using heat pumps essentially. And a car radiator, same idea. Okay. Okay. Dimensions in units. All right. In total, there's 7 fundamental dimensions. Okay. And here they are. Right. So these are the fundamental ones. Any other dimension that you work with is going to be some kind of combination of these. That's really all they're saying. Okay, so here's the fundamental dimensions and units for the USCS system. Here are the fundamental dimensions and the units for the SI system. Okay? All right, and okay. One key point is, when you're working with SI units or USCS units, if you should do, solve the problem completely in the USCS system and solve the problem completely in the SI system. And then at the end, after you've solved the problem, you can make the conversion, right? But these are the units, what they're all based on that. Okay. Okay. And then here's some derived units, right? So Newton, what is a Newton? Kilogram meter per second squared. So if you look at it, it's like, oh, this is like mass. These are the units of acceleration, right? Energy, same thing. A Newton meter, so it's really just Newton, which is this, times meter. So this is just basically same thing, just times meter, okay? And the watt is just this, Newton meter or joule is another way to say it. It's also Newton meter is also a joule. It's just kilograms meters per second cubed. So it's just dividing by seconds. All right, here's Pascal and voltage. So each of these, this is not covered in this class, of course, each of these is just, these are just derived units, just giving you some examples in the SI system. Okay. Our prefixes, all right. So I'm sure you've probably seen these before in Intro to Engineering. What are these? These are just in the SI system, System International. It's just essentially shortcuts, right? Writing it out instead of putting it in terms of like scientific notation. All right. Force units. All right. So you have newtons or force pound. There's also a force mass, pound mass, and this is force This is pound force. Okay. Oh, this should be seconds squared. Sorry. Just this should be uppercase. It should be, you know, superscript here. All right. So F equals ma, right? So you have force is equal to mass times acceleration. And we have the relationship, same thing we have to do here. And just in terms of what it is, right? It's like 1 pound force is one slug, which is 32.17 pounds mass. To get it to go 1 foot per second squared, um, that would give you a 1 pound force. 1 pound force would do that, okay? And that's just showing you the comparison between the two. All right, weight. Weight is just W equals mg, and g is gravitational constant of the Earth, all right? And depending upon which unit system you're using, and this is at sea level, should be sea level. Now you see this, sea level and 45 degrees latitude. So if you're using SI system, it's 9.807 meters per second squared is the gravitational acceleration of the Earth. And if you're using the USCS system or English system, it's 32.174 feet per second squared. All right, so nothing really special about this, I think. Okay, work. So units of work in the SI system is joule, which is just 1 Newton meter. Okay, so either one. And then the English system, it's foot pound. Yeah, okay. All right. Power. Power is just in terms of, well, a common one is horsepower for English system. Power is the time rate unit of energy or work. Okay, so it's joules per second is the unit, which is a watt. 1 joule per second is 1 watt. And then in the USCS system, horsepower is commonly used. Okay, dimensional homogeneity. So this basically just says the units, really what we go through, dimensional analysis is one of the terms that's used. But we want to make sure that whatever units we have on one side of the equation better match the units on the other side, right? And this just gives you an idea that, yeah, okay, this is dimensionally homogeneous because here's my length. Velocity is length over time and times time. So then we have a length unit here. And then this one is, A is just length over time squared. And then this cancels out this time. So the end result, just to show that, yes, this equation is potentially valid or it's a possible valid equation, is that we have length on both sides. Okay, units of length. Okay. Unit conversions, nothing really special about this. Correct number of significant digits. I think in this class we'll do 3 significant digits, right? So basic idea is what you're trying to do. You're starting off with a unit, starting off with some units, and you want to change those units. You use these conversion factors. Each of these conversion factor, of course, has a magnitude of 1, right? The only thing it does is it doesn't change the quantity, it just changes the units. In both cases, right? Okay, system and control volumes. Systems and control volumes. So this is some more terminology we'll need for the class, okay? So what we're going to do is typically we'll go through and we'll define something as a system, all right? Basically this region inside it that we analyze, and then we have its surroundings or environment, and then we have a boundary between the system and its surroundings, okay? So that'll be useful for us as we go and analyze systems. Then we have another term called a closed system. And the closed system is a certain type of system we'll look at, and also an open system. But the basic idea is that whatever's happening, there's no mass leaving it, okay? So this is zero. There's energy going in and, maybe work being done, or, I'd like to push this up, but we have energy potentially leaving it, energy and work being done, but no mass is leaving, all right? So, and here's an example of that. Maybe you heat this cylinder with gas in it, it expands and does work to move this piston up, all right, or plate up, whatever you want to say here, okay? But the real key, this should be inside, now that I see these. Inside, so piston has enclosed gas inside, then heated, all right? See if I can correct those, make those few corrections on the slides. Okay, then we also have what's called control volumes, okay? Now, this one you have mass going in and out of it, all right? So you may, in this case, you may have mass coming in, let's say, and it's pushing this piston up. All right, so these are all called control volumes. And now the boundaries are called control systems. So another bit of terminology as we go through and look at different types of problems. Okay, properties of a system. Okay, any characteristic of it, you know, heat, volume, um, weight, mass. These are all things of pressure properties. Yeah, temperature, volume, mass, and other properties. There's other things that are associated with the electrical resistivity, expansion, velocity, let's say. These are all other properties of a system, okay? These are just characteristics or, things defined of the physical system. Then we have some other terminology. We have intensive properties, okay, this is dependent on the mass, such as temperature, mass of a system. Sorry. So in this one, it's like independent of mass of the system, right? So these are intensive properties, right? And then there are other ones. This extensive basically deals with like total amount of something, okay? So some more terminology as we go through our systems, okay? And continue. And the last one here, this idea of continuum, okay? So we're saying that essentially matter is continuous when we go through and solve problems. And we understand that the idea is like you have a lot of void and you have molecules going around, but we just define and say that the system is continuum, or the substance is continuum for a very large number of molecules, okay? So we just say like essentially it's continuous distribution within the matter, within the space, okay? There's no empty space, right? Just another term. And that is pretty quick overview of like the main concepts without getting into any of the solving any of the examples yet, but I will do that. So that's all for now.